بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. This is section 1.2 and it's about Gaussian elimination. We mentioned this method in the previous section, but let us solve some examples about it. The first example, suppose that the augmented matrix for a linear system in the unknowns x1 up to x4. So the first column represents x1, the second column x2, x3, x4, and here we have the right-hand side, the constant terms in the right-hand side of the equations has been reduced by elementary row operations too. So there was an augmented matrix of the system, and we used the row operations we mentioned in the previous section, 3 row operations, and we reduced this augmented matrix into this form. So this is a final form. You see the first column 1 and everything zeros. This is the leading one in the first column. The second column, this is the leading one in the second column. We used it to make all numbers below and above zeros. This is the leading one in the third column. We used it to make the numbers below and above zeros. And this is the leading one in the last column, in the fourth column. And we used it to make all the numbers above zeros. So can we write the system? Can you write now the system after you reach at this form? Yes, of course. The first equation would be x1. 1 is the coefficient of x1 and the other variables zeros. So 1 times x1 or x1 is equal to 3. Second equation, second row will give you the second equation. x2 is equal to -1. x3 is equal to 0. x4 is equal to 5. So this is the solution of the system. So once you reach this form, you can just have the solution of the system. In each part, suppose that the augmented matrix in the unknowns x, y, z. So here we have x, y, z, okay? X, y, z, and the last column is the column of constants. Has been reduced by elementary row operations to the given reduced row echelon form. By the way, this is called, we call this form reduced row echelon form when we have all the numbers above and below zeros. If the number is below only zeros, not the above, we call it row echelon form without reduced. So solve the system. So this is the final point. Let us write the equations here. So x, the first row will give you x equals to 0. The second row will give you y plus 2z equals to 0. And the last row will give you 0, 0, 0, 0 times x, 0 times y, 0 times z. So the left-hand side is 0, and the right-hand side is 1. Well, 0 equals to 1. This is a false statement. So the solution set of the first system is phi. There is no solution, or the system is inconsistent. While in B, if we write the equations, we have x plus 3z equals -1, and we have y minus 4z equals 2, and we have 0 equals 0. 0 equals to 0 is a true statement. So one of the equations have disappeared. So we have two equations in 3 variables. So there will be infinitely many solutions. For x, the leading one is there. For y, the leading one is there. For z, there is no leading one. So z is the free variable. So I say let z equals t. If z is t, then I can, from the second equation, solve it for y. So y would be what? If you take 4z to the other side, it would be 2 plus 4z. But z is t, so y would be 2 plus 4t. From the first equation, I can solve it for x. x would be -1. If you take 3z to the other side, it will be minus 3z, but z is t. And finally, you can say that t is any real number. So these are the parametric equations of the system because it has infinitely many solutions. In part C, I have two equations, 0 equal to 0. So in fact, I have only one equation left in the system, x minus 5y plus z equals to 4. This is the equation from the first row. The other rows 0 equals 0, 0 equals 0. These are true statements, so they don't affect anything. So we have only one equation left in three variables. For x, the leading one is there. For y, there is no leading one. For z, there is no leading one. So y and z are free variables. So I'll call y t1, for example, and z t2, for example. And I will solve the first equation for x. So x would be 4. Bring 5y to the other side, so it would be plus 5y, but y is t1. And z, when you bring it to the other side, it would be negative z, and z is t2. And finally, I'll say that t1 and t2 are real numbers. So in the solution of this system, we have two parameters, while in the solution of the system in part B, we have one parameter. This is called the parametric equations of the system, and the system has infinitely many solutions. Well, here he says that when we have parameters, like in part B and part B, when the system has infinitely many solutions, this way of writing the solution is called the general solution of the system. So he may ask you in the question, find the general solution of the system. So this would be your answer. This is the general solution of the system. This is the general solution of the system. Okay, when you write the parametric equations, this is also called the general solution because it's general solution, as we mentioned in the first video. You can find now specific solutions, if you like, by replacing T1 and T2 by any numbers. For example, if you put T1 0, T1 is Y, remember? T2 is Z, so 0, 0, find X now, X would be 4. So this is one of the specific solutions, okay? And you have infinitely many specific solutions. So the general solution, when you see the parameters, okay? When you have the parameters like this is called general solution. Homogeneous systems, what would happen with homogeneous systems? The constant terms would be always zeros. So notice the right-hand side would be zeros. So we have a1x, b1y equals 0. There are no constants, okay? So when you write the augmented matrix, you will have here zeros, 0, 0, 0. 0, 0, 0, 0. Everything would be zeros. It would be 0 in the right-hand side, okay? When we have such a system, we call it a homogeneous system. So always see x1, yeah. So for homogeneous systems, if we consider two equations in two variables, so we are in a plane like this. So notice that if you put x0, y0, that's a solution of the system, which means that the trivial solution is always there. The trivial solution is always there if x is 0 and y is 0. So you will have 0 equals to 0. So all putting, notice this, putting all variables equal to 0 will give you a solution of the system. It's a solution, and they call it trivial solution, okay? The other possibility, the system has infinitely many solutions. Here, notice, for example, here in the graph, I have this line and this line. Since the equation always equals to 0, so the graph of the equation passes by the origin. Also, the graph of the second equation passes by the origin. So they intersect at the origin, 0, 0. Okay, so if you replace x by 0, y by 0, there is a solution, the trivial solution. If you have one equation, if the two equations represent one line, then we will have infinitely many solutions. So for homogeneous linear systems, there are two possibilities, either one solution or infinitely many solutions. Uh, there is no possibility the system is inconsistent or there is no solution, because there is always the trivial solution. The trivial solution is always there. So remember, for homogeneous systems, we have two possibilities, not three possibilities like the non-homogeneous systems. Non-homogeneous systems, there are three possibilities. The system could be inconsistent, no solution. For homogeneous systems, no, we have two possibilities only, because the system is always consistent. Whenever we have more unknowns than equations, immediately you will have infinitely many solutions. Let us solve some exercises. He asks here to solve this system by Gaussian elimination. So the first step would be to write the augmented matrix. The variable, you can write rows or columns as you wish. I will use columns. So the column for x, the coefficients of x, 1, 2, -1, 3. These are the coefficients of x, okay? The first variable. The second variable y, I have 1, 1, 2, and there is no y in the last equation. Z, 2, 2, -4, and no z in the last equation. For w, I have -1, the coefficient, -2, 1, and -3. And then I have the constants, -1, -2, 1, and -3. So this system is non-homogeneous because the numbers on the right-hand side are not zeros. Well, this is the augmented matrix. Remember, for Gaussian elimination, this number should be 1. And it is, we call it the leading one in the first column. Well, it is 1, so that's good. Since it's 1, I go to the next step. What is the next step? Use this one to make all the numbers below zeros. So when we use 1 to make 2 0, how? We multiply row 1 by -2 and add to row 2. Okay, and how to use the 1 to make -1 0? We add row 1 plus row 2. And how to make the 3 0 using this one? I multiply row 1 by -3 and add it to row 3. By using these three operations, we will get a new matrix. The first, but with the same solution. The solution of the system will not change. That's why you are using only these three types of row operations. Okay, -2 plus 2, 0. -2 times 1, -2 plus 1, -1. -2 times 2, -4 plus 2, -2. -2 times -1, 2 plus -2, that's 0. -2 times -1 is 2 plus -2, that's also 0. Okay, the third row, we will change the third row by this row operation. R1 plus R2, 1 plus -1, 0, 1 plus 2, 3, 2 plus -4, -2, -1 plus 1, 0, -1 plus 1, also 0. The last row, -3 row 1 plus row 3. -3 plus 3, that's 0. -3 plus 0 is -3. -3 times 2, -6 plus 0, -6. -3 times -1 is 3 plus -3, that's 0. -3 times -1 is 3 plus -3, that's also 0. So this is the new matrix. And now we finished from the first column. We have 1 and the next, the below entries are zeros. Now we go to the next column, the second column. And we start, also we look to the second row. This number should be 1, positive 1. So how to make it 1? Multiply row 2 by -1. So we will have this new matrix. 1, 2, 0, 0. And here I have 0, 3, -2, 0, 0, and finally 0, -3, -6, 0, 0. Okay, this number is 1, and it is called the leading one. Gaussian elimination, uh, make the numbers below zeros. Use this one to make the numbers below zeros. If we are using Gauss and Jordan, then we will make this one also 0 using this one, the leading one. So I'm using Gaussian elimination, so I will make 3 and -3 zeros. How? I'll multiply 1 by -3. So -3 times row 2, when you add it to row 3, you will get a 0 here, and you change all of the row with this operation. Now this is -3. How to make it 0? I multiply row 2 by 3. So 3 row 2 plus row 4 will make this number 0. Now I'll get a new matrix with the same solutions. The first row is not changing. The second row is also, there is no operation to change it. Now the third row, notice that one important point. I'm using the second row to change the third and the fourth. Whenever you have zeros in the second row, so for example, I have 0 here, this 0. It will not change any number below. Why? Because if you multiply this 0 by -3 or by 3 or by any number, it would be 0. Add it to row 3, you will get the number in row 3. You understand? So nothing will change below this 0. Also, I have 0 here, so these zeros will remain the same. I have 0 here, so these zeros will remain the same. You can do the operation usually, as usual, and you will get zeros here without any problem. Now, -3 plus 3, I have 0 here. -3 times 2 is -6 plus -2 is -8. -3 times 2, -6 minus 2, -8. That's the third row. The fourth row, 3 times 1 is 3 minus 3, that's 0. 3 times 2 is 6 minus 6, that's 0. So now I have the last row zeros. So I understand now that I still have 4 variables, but 3 equations. So I'll have infinitely many solutions. This system will have infinitely many solutions. Now, the second row is finished. The second column is finished according to Gaussian elimination. So I go to the third column, and the third row, this number should be 1. This number, notice that all of these numbers are in the main diagonal, on the main diagonal, okay? On the main diagonal, these numbers are the leading ones. Okay, so how to make -8, 1? Just divide row 3 by -8. So I'll have 1, 1, 2, -1, -1. I'm only changing row 3 here. So I'll have 0, 0, 1, 0, 0, and 0, 0, 0, 0, 0. Okay. Now, Gaussian elimination, I should use this one to make the number below 0. I have it already 0, so that's excellent. If you are using Gauss and Jordan, you should use this one to make these two numbers, 2 and 2, zeros. But I'm using Gaussian elimination. Okay, I finished from column 1, column 2, column 3. I have 3 leading ones, and all the numbers below them are zeros. Now, the next step, this number should be 1, but it is 0. I cannot change it to 1. How can you change numbers to 1? Either by dividing by the number itself, or by interchange with a row below. There is no row below here, and this is the last row, and this number is 0. I cannot make it 1. So that's it. This is the last form. We call this form the row-echelon form. This is the row-echelon form. So write the equations again. X, Y, Z, W. Notice the variables are X, Y, Z, W. So the first equation would be X plus Y plus 2Z minus W equals -1. This is the first row. The second row, I have no X, but I have Y. Y plus 2Z equals 0. The third equation comes from the third row, X, Y, and nothing. Z, I have Z equals the right-hand side is 0. And the last equation, 0 equals to 0, which is a correct statement, a true statement, but it doesn't give any information. So I know that Z is 0, and I have W as free variable because it has no leading one. So let W equals T. And I have Z0. So what would be Y? Well, if you look here, Z is 0, so Y is also 0. So I have Y 0 and Z is 0. So if you now go to the first equation, you use back substitution, okay? Now Y is 0, Z is 0, so X is equal to what? There is negative 1, and there is negative W. Take negative W to the other side, it would be plus W, but W is T, so T, and you can say that T is belongs to R. So this is the general solution of the system, or the parametric, these are the parametric equations of the system. You can check your answer, and your answer is correct by choosing a specific solution. For example, if you choose T to be 0, so you can understand that X is negative 1, Y is 0, Z is 0, W is 0, because W is T, you chose T to be 0. So this must be one of the solutions of the system. So if you replace X by -1, notice here, negative 1 equals negative 1. If you replace X by negative 1 and all the other variables 0, negative 2 equals negative 2. If you replace X by negative 1, negative 1 times negative 1 is 1, and all the others are 0. If you replace X by negative 1, this would be negative 3 equals negative 3, and W is 0. So in fact, this point satisfies the system. So this is one of the solutions of the system. You can choose another solution and make sure that your answer is correct. This is the general solution of the system. Solve the system by Gauss and Jordan. Okay, now we will solve using Gauss and Jordan. As usual, the first step is to write the augmented matrix. There is no A in the first equation, so I have 0, then 3, then 6. For B, I have negative 2, 6, 6. For C, I have 3, and negative 3 and 3, and the numbers 1, negative 2, 5. So this is non-homogeneous system. This number must be 1. It is not 1. It is 0. Okay, I cannot divide by anything and make it 1. So I have to interchange it with a row below. Okay, look carefully to these two rows now. I have 3. I'll need to change 3 to 1, so I'll divide by 3. If you divide by 3, I'll get here negative 2 over 3, 1 fraction. To make 6 1, I'll divide by 6. I'll have 3 over 6, that's half, and 5 over 6. I have 2 fractions, so I prefer to interchange row 1 with row 2. So row 1 would be 3, 6, negative 3, and negative 2. So this is interchanging. Interchanging two rows does not change the solution of the system. 6, 6, 3, 5. And now I can make this 3, 1 by dividing row 1 by 3. Okay, so I'll have 1, 6 divided by 3 is 2, negative 1, and negative 2 over 3. And the second and the third rows remain the same. And now I made this number 1. I have a leading 1 now. I use it to make the numbers below zeros. This is 0. Thank you. So 6, make 6 0. How? Negative 6 row 1 plus row 3. First row as it is, 1 to -1, negative 2 over 3. This is 0. There is no change in it. And now negative 6 plus 6, this is 0. Negative 6 times 2 is negative 12 plus 6, this is negative 6. Negative 6 times negative 1 is 6 plus 3, that's 9. Negative 6 times negative 2 over 3 is 4. You can use the calculator. Okay, 6 over 3 is 2 times 2, 4. 4 plus 5, that's 9. So now I have this matrix. 1, 0, 0, the first column finished. Now I go to the second column, second row, this number must be 1. I have to make it 1. To make it 1, I have two choices. I'll divide by -2, then I'll have two fractions here, or uh, I interchange it with row 3. If I interchange it with row 3, I'll have to divide by -6. So I'll have 1 here, but I'll have also two fractions here. So there is no need really to interchange. Just I will divide row 2 by -2. It doesn't make it easier by interchanging. So I will divide row 2 by -2. I'll have first row as it is. And the second row, I'll have 1 here, and then -3 over 2, and then 1 over -2, and the last row as it is. Now, using Gauss and Jordan, you have a leading one in column 2, which is this one. You have to use it to make these two numbers zeros. So -2R2 plus R1 will change 2 to 0, and 6R2 plus R3 will change this -6 to 0. The new matrix would be, the second row is not going to change. Now notice I'm using the second row to change row 1 and row 3, and this is 0. So if you multiply this 0 by any number, by -2 or 6, it would be 0. Add it to 1 or to 0. So 1 will remain as it is, 0 will remain as it is. And that's why if you follow these steps, you will not change column 1 again. Okay? You want to keep column 1, 1, 0, 0, of course. So you will do that if you follow exactly my steps. All right. So -2 plus 2, that's 0. -2 times -3 over 2 is 3. Plus minus 1, that's 2. -2 times 1 over -2 is 1. 1 minus 2 over 3 is 1 over 3. Now the last row, 6 plus minus 6 is 0. 6 times -3 over 2 is -9 plus 9, that's 0. 6 times 1 over -2 is -3 plus 9, that's 6. Now I have the first column finished. I have a leading 1 and the numbers below zeros. In the second column, I have a leading 1 and the numbers above and below zeros because I'm using Gauss and Jordan. Now the next step, this number should be 1. Well, I cannot make it 1. It is 0. I cannot change it to 1. I have nothing below, and I cannot divide. If you divide by 0, that's not going to change it to 1. 0 over 0 is math error. So let us write the equations. Well, the equations would be, what are the variables A, B, and C? So the first equation is A plus 2C equals 1 over 3. Second equation, I have B, -3 over 2C equals -1 over 2. The last equation, I have zeros here. 0 times A, 0 times B, 0 times C equals 6. Well, 0 equals to 6 is not a true statement. So the solution set of this system is phi. This system is inconsistent. It has no solution. Well, let us have another final example. Solve the given linear system by any method. I will solve it by Gaussian. I prefer Gaussian elimination. So I will use first, let me write the augmented matrix. W, I have 1, 2, -2. For X, there is no X here, but I have 3, I have 1. For Y, I have -1. 1 and 3. For Z, I have -3, 1, and -2. And the constants are 0. So this is a homogeneous system. It's a homogeneous system, and we have 4 variables and 3 equations. So the system has infinitely many solutions. Okay, that's, you should know, when you have a homogeneous system, number of equations less than number of variables, you must have infinitely many solutions. Okay, this number should be 1. It is 1. We use it to make the numbers below zeros. So negative 2R1 plus R2 and 2R1 plus R3. The new matrix would be 1, 0, minus 1, minus 3. Of course, these zeros will not change at all. Always they will be zeros because if you multiply any zero by any number below it, add it to the number, the entry below it, it will not change. Okay, negative 2 plus 2, that's 0. 0 does, I'm using R1 here, so 0 will not change, the 3 will not change, the 1. Okay, negative 2 times negative 1 is 2 plus 1, that's 3. Negative 2 times negative 3 is 6 plus 1, that's 7. And the last row, 2 plus minus 2 is 0. 2 times 0, 0 plus 1, that's 1, okay, to check. 2 times negative 1 is negative 2 plus 3, that's 1. 2 times negative 3 is negative 6 plus minus 2, that's negative 8. I finished from the first column. The second column, this number, I need to make it 1. Well, it is not 1. To make it 1, I have two choices. I can divide by 3. I'll have 7 over 3 here, a fraction, but I have 1 below. So why should I have fractions? Just interchange row 2 with row 3. So I'll have 1, 0, negative 1, negative 3, and 0. And I'll have 0, 1, 1, negative 8, and 0. And I'll have 0, 3, 3, 7, and 0. Now use this number, which is 1, to, this is the leading one, to make the 3 zeros. So negative 3, row 2 plus row 3. The first row is not changing. Second row is also. I'm just changing the last row here. This will not change because I have 0 here. Also, I have 0 there, so this will not change. Any 0 in row 2, you just write what is below it as it is. Okay, negative 3 plus 3, that's 0. Negative 3 plus 3, again 0. Negative 3 times negative 8, that's 24. Plus 7, that's 31. Okay, so this is the new matrix. The first column is good. I have 1 here and below zeros. The second column is good. I have 1 here below zeros, even above zeros. Okay, now the third column and the third row. This number, I have to change it to 1. I have to make it 1 if I can. Well, I can't because it's 0. I cannot make it 1 by dividing or by interchanging with a row below. There are no row below, no rows below this row. So that's the final step. Okay. Well, it is not, in fact, the final step. Pay attention to this point. If you cannot make this number 1, go to the next number in the row. Okay, I'll mention this again. So I was discussing the third column. I needed this number to be 1. I couldn't make it 1. What to do? I am in the third column and the third row here. Okay, I cannot make this number 1. Go to the number to the right in the third row. This number, make it 1 in this case. Okay, this is the Gaussian elimination or Gauss and Jordan. If you have such a situation, if you cannot make this number 1, go to the number to the right. Continue in the third row. Okay, so 31, it is easy to make it 1. I'll just divide by 31. So the new matrix would be 1, 0, negative 1, negative 3, and 0. Here I have 0, 1, 1, negative 8, and 0. I'll have 0, 0, 0, 1, and 0. This is an important example, by the way, because you have seen this new idea here. Now, where are the leading ones for each variable? Well, for the first variable, which is W, this is W, X, Y, Z. For W, this is the leading one. For X, this is the leading one. For Y, there is no leading one. It has to be here. This cannot be leading one because there is only one leading one in a row. Okay, in a row, there is only one leading one. In a column, there is only one leading one. So for Y, there is no leading one. For Z, there is a leading one, which is this one. So if you use Gauss and Jordan here, you should continue to make -8 and -3 zeros using this leading one. But I'm using Gaussian elimination, so I'll stop here and write the equations, okay, the system. So I have the first one will give me W minus Y minus 3Z equals 0. The second one would be X plus Y minus 8Z equals 0. And the last one will give me Z equals to 0. Y is the free variable. So I will let Y equals to T. And I have Z equals to 0. So what would be X from the second equation? Back substitution. Third finished, go to the second. Y is 0, Y is T, sorry, and Z is 0. So X is negative Y. So X is negative T. Now go to the first equation. Z is 0. Y is T. So W would be equal to Y or T. And T is a real number. So this is the general solution of the system or the parametric equations of the system. I hope you will benefit from this video. And this is really the main idea in section 1.2. Have a nice time.